Hello. 1 second. I hope you can hear me. So, any doubts that you have? Anything you would like to resolve them first? So you can type in the chat or tell me what topic you have doubt about, and then we can discuss. Uh, mm, if there are okay. Uh, Yeah, any doubts regarding? So this week we will cover. This is week 7, and we will cover issues of actually diversity and trading. So this is, uh, if I have to like lecture number wise, it's lecture roughly 29 to 33. So these are the lectures. So any doubt with these lectures or previous lectures, anything that you would want me to cover, um, I can help with that. Otherwise, I'll discuss. Mm, okay. Yeah, somebody joining. Mm, uh, okay. So I hope you can all hear me. And so again, any doubts? Otherwise, I'll start discussing um, similar to assignment questions as I normally do. Uh, mm, and then, okay, and then continue. Sandeep. Um, this week we are continuing from previous week. So in the previous week we had studied we had mainly studied about fading and Doppler shifts, and like in fading in general, how fading happens. and various kinds of fading. And so those topics will study. We recap. So and how and the notions of uh, so uh, so there were notions of frequency selectivity and fast fading. And so I'll just so there is one question in the assignment regarding that. So I'll just revise the concept here very quickly. That we have two axes mainly on which we decide. One is the uh, coherence bandwidth, uh, bandwidth, which we denote as BC, and the other is the coherence time, which we denote as TC. And we have sampling time, TS, and the uh, symbol or the signal bandwidth, BS, right? And we have this kind of we can divide it into 4 zones, right? If I just draw it a little neatly. We can divide it into 4 zones. That if my coherence time is smaller than the sampling time, right? Let us recap. So yeah, so this is fast and slow fading. So if my coherence time is smaller than the sampling time, it means that my channel will change at the same for the same spectral characteristics, for the same everything being the same. The channel will change faster than the time I take to send a symbol. So that means this is fast fading. Here FF stands for so on this axis FF is fast fading and SF is slow fading, right? So we had this notion. So left of this sampling time, we'll have fast fading. Right of this sampling time, we'll have slow fading because the channel coherence time is higher than the signal propagation time. So which means that by the time the signal has propagated, the signal has gone out into the medium, the channel hasn't changed that much. So we can consider these channels as slow fading. On the other side, in the frequency spectrum, if the channel bandwidth is higher than the coherence bandwidth, it means that if the signal bandwidth, so just if the signal bandwidth is higher than coherence bandwidth, it means that um, the the signal in frequency spectrum, the channel's response in frequency spectrum fluctuates faster than the bandwidth of the signal, which means that the signal experiences different different channel gain magnitudes for different frequencies. So that is why this is frequency selective, and this is frequency flat. So again, FF on this axis, this is frequency flat, and this is frequency selective. So I'll just define the terms again. Here, TS is symbol time, and BS is the signal bandwidth in frequency domain, right? So yeah, so this is kind of a recap of what I was discussing, the very initial part. So I just drew the same diagram again, and so because let's see, so we can do we have a similar question in the assignment, which is why I thought let me recap this. So let's say channel coherence time is said to be um, let's say 10 microseconds, right? 10 microseconds, and coherence bandwidth is 1 megahertz, let's say, right? And you are told that this is 16 quant. We are using uh, like, yeah, we are using 16 quant, let's say, modulation, 16 quant modulation, right? So, and throughput, uh, the throughput or bit rate is 1 Mbps throughput. This is something, or let's make it actually higher. Coherence bandwidth is okay, 1 megahertz. Let's make it like 10 Mbps. Okay, 10 Mbps throughput we're getting, right? So we are asked describe the channel. So this is let's say question 1. Describe the channel response. How do you describe the channel? You describe it as either, you use either of these four words. Fast fading or slow fading, that is one distinction you make, and then you decide whether it's frequency flat or frequency selective. Okay, so you choose whether the channel is fast fading or slow fading on time axis, and then on frequency, so whether the frequency flat or frequency selective. All right. So let us evaluate this. So we have here that the bit rate, um, the bit rate here is RD, if I have to write it. This is 10 Mbps, right? Which means, so, but how many bits are there in a symbol? So this is 16 quam. 16 quam means 16 means 2 to the power 4, right? Which means 4 bits per symbol. 4 bits per symbol. So if this is my bit rate, my symbol rate will be, because 4 bits comprise one symbol, so my symbol rate will be 1/4 of the bit rate, right? Because if I send 4 bits, I'm sending one symbol. So my symbol rate will be 1/4 of the bit rate, which will be 2.5 mega symbols per second. Now I'll use this somewhere because I know the symbol rate, so I can find out the symbol time, which is uh, 1 by 2.5 microsecond. So I believe this will be 0.4 microsecond, if I'm not wrong. So I hope this part of the calculation made sense, right? And let me reduce the coherence rate even lower. It's a very highly fluctuating channel. But even then, we see that the symbol time is less than coherence, right? Symbol time is less than coherence time, which means that this is so this is one thing that we know. And now let us figure out the bandwidth of the signal, right? So 1 second. The signal bandwidth is actually equal to the rate, because in a way, so this is the rate is kind of the sampling frequency of the signal as well. So I'm sampling signals at this rate, and so the bandwidth uh, is like bandwidth is also defined in per hertz, right? So normally, if I send a symbol, it's in like it's it's at the carrier frequency. But then when I spread out the symbol, or like when I'm sending symbols at a certain rate, it means that I'm like generating it at a certain frequency, right? So anyway, so let us the coherence bandwidth is 1 megahertz, and uh, 1 megahertz because and my symbol rate, which is equal to the the bandwidth also. This is equal to 2.5. This implies signal bandwidth is equal to 2.5 mega symbols per second. So per second denotes hertz. Because I am generating symbols at this particular rate, which means I also have to spread it in frequency like this. So then this coherence frequency, this signal bandwidth is also is greater than the coherence bandwidth, right? Because coherence bandwidth I'm given to be 1 megahertz, and signal bandwidth I'm thinking it is 2.5 megahertz. So so coherence time is less than greater than signal transmission time or signal transmit duration. Symbol transmit duration. So this means that the channel is um, so we are sending a signal faster than the time that it takes to change. So this means that it is slow fading, right? Slow fading or SF. And here the signal bandwidth is greater than the signal uh, than the than the channel's coherent uh, than the channel's coherence bandwidth, which means that uh, the channel will change in the frequency domain. If you take things, then the channel will change uh, before the signal is completely transmitted. So that is why this will be a frequency selective frequency selective sample. So combining, we'll have this channel as slow fading plus frequency selective. This will be the answer for this question. But in general, you can repeat this for any values that you need to find out. This is the main quantity that you need to find out, which is the symbol rate. And so since this is like digital signal processing, so the frequency at which you are sampling a certain symbol, that is the frequency with which you have to spread out the signal as well in the frequency domain. So your frequency domain spectrum response will have a coherence bandwidth, which is this. Will have a bandwidth of the same value. So, it will be it will be the same value, and uh, and then symbol duration is nothing but so if we write down the formula, symbol duration is nothing but 1 by RS, 1 by symbol rate. So you just have to then compare TS and TC, the coherence time which you've been provided, which is 1 microsecond, and you have to compare the coherence bandwidth which you have obtained, the coherence bandwidth which you are given, and the signal bandwidth which you have obtained. So and then you make a decision. Then you describe the channel as medium. Okay. Um, This part is here. Um, how to find average SNR if ECG is used? What is ECG? If you can say, average SNR is essentially so. Um, so if you have a fading channel, so you have some channel like your output channel output is equal to y equal to some fading gain, some complex fading gain, let's say x plus n, right? Let us not consider interference for now. So you have your signal, your SNR. SNR will be this signal term um, will be instant SNR instantaneous. Let's say instantaneous SNR will be signal term divided by noise term, right? And then so this signal term is so I'm writing this in this way, where PS is signal power, which is modulo of x squared, and Pn is noise power, modulo n squared. Now, essentially, if you have to take expectation over FNR, instantaneous, okay, then your PS and PN are constant. Signal power and noise power are constant, and so you have to take expectation of the over the fading coefficients, right? This is your fading coefficient. So this is how average. So this is what you will call. This is your SNR average, and so this is. So then to calculate average SNR, you need to calculate average value of the complex scale. I don't know if this is what you're looking for. So this is how you find average SNR. Normalized capacity of channel. This one I'm not sure. What are you normalizing against? Like, are you having some base reference? Like this part I'm not sure what you're referring to. But anyway, so this was discussion on fading, and I won't discuss more on this. So again, second question might be let's say you have a frequency, you are given a frequency plot like this, some signal, some output signal, y is your output signal after passing through a channel, and it has a response somewhat like this. So there is a carrier frequency fc it is centered around, and there is some this is it. And there are two cutoff points here. Let's say some fc plus fd and fc minus fd. So all the signal power is in this room. So what kind of signal is this? So let's say your options are A, P or LOS, line of sight, B Doppler, Doppler is fading. The answer in this case is Doppler shift, right? Because you in fading you have no control. Things can like if there is frequency selective fading, then it can take any shape. It can distort the frequency spectrum. But in Doppler shift, we know that Doppler shift can be maximum of Fc plus Fd or Fc minus Fd, where Fd is something like V by C carrier frequency, right? So So FD max, let's say. FD max is this. And I should remember this FD max. FD max. Why max? Because FD normally is V by C FC times cos theta, where theta is the angle between the relative velocity of Tx and Rx and the direction of propagation of the radiation. If this is Tx, this is Rx, then this angle is theta, because let's say the transmitter is moving in a general direction theta. Now, when this theta is 0, then we can have maximum positive Doppler shift when it's moving towards the receiver, and when it's moving directly opposite to receiver, then we'll have maximum negative Doppler shift. So any Doppler shift, any theta in intermediate, so between 0 and 180 degrees, it will have some intermediate value, and so we'll have the frequency in this range. So this kind of graph you should be able to interpret. So, but the main focus of this week's discussion is on diversity gain and all of that. So I'll come to this. Quick conceptual question that I have a system that is, let's say, noise limited. So I'm told that system is noise limited, right? So which of the following, so I am writing two statements here.
Excuse me, sir.
Yeah.
Sir, what was this second question?
Second question, I'm just trying to say that like you have a signal X of F, you are passing through channel H of F, and you are getting an output Y of F, right? And you are observing Y of F. So you know that, let's say, X of F was just, let's say, single tone with carrier frequency F2. So your Y of F, you are finding that it looks like this. So some signal bounded between Fc minus Fd to Fc plus Fd. Then what is the nature of the channel? Like, is it a pure line of sight channel, or a Doppler shift channel, or a fading channel? So as I explained, for pure line of sight channel, your carrier frequency would not change. Like, you will get the exact same, like if your line of sight path is not blocked, then you will receive the signal in exactly the same form, in like with just one tone Fc. But there might be some antenna gains or losses, whatever. Magnitude might change, but frequency won't change. In fading case, in frequency selected fading especially, then your frequencies might get distorted, and like it can look very different. The signal can look very different. But in like this is, for this case, the answer was Doppler shift, because you have your frequencies bounded between an Fc plus Fd and Fc minus Fd, and where Fd max is this V by C Fc, where V is the velocity of the transmitter. So we know this, right? Doppler shift, the formula is V by C Fc cos theta, and so it can take maximum value V by C Fc and minimum value minus V by C Fc. So it will be within a range. So that is the
So when
range
the frequency of signal is Fc only, then amplitude will be maximum.
Yeah. Maybe not. Maybe this is not accurate here. We can roughly say that this might not be the case. Might not be the case. That was where I drew it that way, but it might not be the case.
Okay.
Might not be the case. Yeah. Might be anything. But it, like in focus was, it is bounded between certain frequency range, so it is Doppler.
Okay, sir.
Okay. We can just refer to notes also. Some more discussion is there. Okay. Moving on, you are given a noise limited scenario, and you are given two statements here, and you have to say like which statement is true. You are asked which statement is true. Firstly, you are said that C by N is much less than C by I. And second statement is C by N plus I approximately equal to C by I. So, well, like it's not this way, but let's say you are asked true, false for both. So you have to say whether A is true or A is false. You have to say whether B is true or B is false. So let's talk about A first. Is A true or false? So C is just to be clear, C is the channel gain direct signal. Direct signal. N stands for noise. I stands for interference or interference from other users, right, or other signals. And so you have to first give me answers, right, for A, true or false, and for B, true or false. So do we have any answers? BDR of Nakagami M scheme, that is a little complicated. I don't think you have it in this week's exercise. I myself have to revise it a bit. It is
false, sir.
Yeah. A is false. A is false, you are saying.
False.
And B? Any answers for you? Somebody asked me B or for Nakagami and Fennel. This I need to look into as well. It is a little complicated actually. Like for relay channel, if you know how to find BER, then you have to use a lemma called Alzer's lemma, and then from there you can calculate. But it is not trivial. It's a little complicated. I don't think it is coming right in this week. Maybe next week it is coming. We can cover it then. But okay, the answer should be actually A is true. This one is wrong. A is true, and B is false. B is false. I'll tell why. So by noise limited, see. So what is my SINR expression? So this is signum to interference plus noise ratio, right? So I have signal power, interference power plus noise power. By noise limited, what I mean is, so noise limited means that my noise dominates interference, right? My noise dominates interference, which means if N is much greater than I, which means that if I flip it, which is C by N. Firstly, let's just take inverse of this. So 1 by, if N is greater than, much greater than I, then 1 by N is much less than I, much less than 1 by I. And if I multiply C on both sides, and we know C is a positive quantity, the signal power. So C by N will be much less than C by I, right? So this is actually true. So this is when it's noise limited. So noise limited means noise is stronger than interference. So that is why the noise the noise dominates, and so C by N is much less than C by I. So if you can flow it from here, if N much greater than I, then C by N will obviously be much less than C by I. And since N is much greater than I, over here in the denominator, we can ignore I because I is much, and we can write it as C by N, because this is noise limited. And C by N, and here the question was C by I, which is wrong. We cannot write it as C by I. So it is equal to C by N. So that is why A is correct and B is incorrect. Is this clear?
Sir, means noise limited signal, noise limited channel means noise is less, na?
No, noise limited. Okay, I can understand why you think like this, but that is not the standard way of. So standard by limited here, what is meant is that it's not like noise is less. It's like noise is the limiting factor in this channel. Like what we are trying to see, to think it in this way, that I'm trying to send a signal over a channel. What is stopping me from sending it? So there are two things that can stop you. There are three things actually. There is interference, there is noise, and the third thing is fading. So let's leave aside fading for now. Mainly interference and noise, right? So in interference and noise, there like depending on whichever is dominating, we assign the channel as interference limited or noise limited. So if the channel is noise limited, it means that noise is the limiting factor in the channel. It is because of noise that I'm not being able to send anything over the channel. So that means that noise is stronger than interference. If I'm saying interference limited, it means that interference is stronger than noise. That interference has a stronger effect than noise. And so that is why, because the channel has interference, I'm not being able to send anything. Is it clear now? So that is the standard nomenclature that is used. If noise limited, it means that noise is much greater than interference. Noise is much stronger than interference. If it's interference limited, then interference is stronger than noise. We are just trying to identify which of the two is a limiting factor.
Okay, sir.
Smith method and Clark-Gans method. I think the details I also don't remember completely. It is like two different methods of not two different methods. It's actually the same thing. So like it's we are essentially trying to find out correlation between different channels, right? So in like just taking from the lectures only. So I have some so in the so I have some white Gaussian signal. So I'm sending white Gaussian signal. So this is white Gaussian signal. So this is what I'm passing this through a tap delay channel HD. So I'm passing it through a tap delay channel HD. So this is in digital domain, and I am so like I can firstly pass it through in continuous time. I can do it this way. I can pass it through channel H of T, and then I can have a phase shifter, like just which multiplies it by a J. So it just essentially adds an pi by 2 phase here. So over there, I will basically get this kind of a signal. So I'll have one real part over here, real signal over here. And this is, 1 second. So I'll have one real signal, another will be some imaginary signal, and so I'll be adding them. Imaginary signal, and I'll have this real plus I times imaginary signal. Right? And then I'll use this, so some kind of correlation I'll do, so that I'll essentially, using this method, I'll try to obtain this quantity, delta t over tau. So I'll try to obtain the correlation of HD t comma tau and HD star t plus delta t over tau. I don't think details for this are needed, especially for the assignment. So this is the, let's say, the main idea of Clark and Gann's method is that let us take real and complex part, and through the channel let us pass this wide Gaussian signal, and then let us take real and complex part and do some correlation between them, so that uh, we can so at every time delay, if we use different filters, so we can get the so different. So let's say we do different filters. Actually, it's applied. Let's see. The channel will change after every time t. So if there is some delay here, let's actually write it this way. So if there is some delay here, some delay tau, some delay tau is there. So then it delays the signal, right? So we have ZRT plus ZT plus actually, which is like ZT plus Z of T minus tau, something like that, right? And then we take correlation, and then we can figure out the value of the correlation of channels, something like that. Now, Smith's method is nothing but we convert it into digital font of Clark and Gann's. So that's pretty much all you need to. By digital form, what I mean is, now instead of HD of t, instead of time delay, instead of continuous time responses, you will take sampling of it at some intervals, and so you will have tap delay response of the channel, and you will be replacing the actual analog delays by some kind of phase shifter. So that is why this e to the power j term will come, and like e to the power j pi by 2 phase shift, which is j. So these phase shifted terms will be there. So you will get your eventual signal as whatever I wrote in there, which is real part plus j times some imaginary part. And again, you take correlation, so you will now get instead of like analog correlation, you will get like digital channel correlation. So you will have something like something like now channel correlation will be in terms of digital values. So it will be expectation of channel gain at n comma tau, and because you are sampling the time, and then n plus m comma tau. So you are sampling the gains, right? So this is just when what you are doing is, when instead of doing x of real part of n convolved with h d of n, you are you will effectively be doing something like FFT. You'll be taking FFT. You'll be doing this operation in frequency domain basically. You'll be taking FFT over XR of n uh, over the real part of the signal, and you'll be multiplying it with the, instead of doing convolution, what you will be doing in Smith's method. So this is convolution is actually Clark and Gans method, right? Actually, I shouldn't. This was fine actually. This is tap delay response of channel. All this is fine. So you will have J, you will have real part, and you will have, this will give you imaginary part. So this is so you have imaginary part, and then you will have combination of real and imaginary. But all of this operation was happening in time domain. So that is time domain. Now in frequency domain, what happens? I shouldn't write it as a digital form. Let's listen to frequency domain equivalent. In frequency domain, you will be taking firstly FFT of the. So instead of convolution, what you will do is you will essentially be doing x, something like x times x, right? So convolution becomes multiplication in frequency domain. And then this final output is in frequency domain. So you will do a Fourier inverse. Fourier transform, something like this, right? So you will convert it back into time domain. So that you can also write it as, now in digital communications, you will write it as firstly an IFFT operation in the end. But initially you will do FFT of the time response of the real signal. And then you will do FFT of the time response of the channel. And then you will multiply the FFTs and finally take IFFT over both of them. So this is the Smith's method. So this is the Smith's method. So Clark and Gern's method corresponds to this, where you just take plain convolution. Smith's method corresponds to this. Smith's method corresponds to this, where you also do all of this FFT, IFFT, and then get your output. So that is the difference. And so here, instead of doing your direct convolution, if you are doing FFT and IFFT, then it actually is a very efficient model. And so you have lower complexity. The Smith method is lower complexity. But so Smith's method, FFT and IFFT are efficient methods. So Smith's method has lower complexity. But it also has like limited duration, right? Because you cannot generate like if you are using NFFT in your FFT algorithm, you are using N gradation of FFT, and sampling time is TS, which means that you can generate. You are trying to generate a random fading channel, but you can generate fading waveform for. So generate for 2 to the power n times this sampling time. Because you can generate, like, using n FFT, you can generate 2 to the power n symbols, and you can sample at this time. So you can generate for these many seconds. So in 1 second, you can generate 2 to the power n symbols, which is in them, so on and so forth. But there is a limit. So in Clark and Gann's method, which is without FFT, there is no limit because we are just doing ideal convolution. So we can generate fading channel for any length of time. So that is, but this is lower complexity. That is one idea. So that is the main idea. Now, if there are problems, you can refer to lecture 31 for more details. Okay. Okay. Now you are told right. You are told that any further questions? Smith and Starklands, you can refer to lecture 31. And most of the questions in the assignments on these methods are very straight textbook questions that you can answer straight from theory. You are typically not asked to derive all of these things. So I'll go to the more important part, which is diversity, where more conceptual kind of questions are there. And small question on J model, but it's okay. So there is one, before that, there is one question on Jake's model. So, so you have a channel, Doppler shift channel, like Doppler, you have a channel with a Doppler shift map of 1 kilohertz. You have a channel with a Doppler shift maximum of 1 kilohertz. And what else? And you're given that you have a Jake model. You are told that simulation, you are doing a simulation of this with Jake's model. Jake's model, which, let's say, 100 oscillators. Oscillators. So we told what are the oscillation, what are the oscillation frequencies? You are asked what are the oscillation frequencies. You are asked what are the oscillation frequencies. And so how will you answer this question? So you are told that like there are 100 oscillators. So in Jake's model, you have like the number of the oscillation frequencies in a Jake's model are given by this formula. This is there in the lectures, lecture 29, I think, 29 or 30. You can say that for Jakes, like there are various correlation models for a channel and correlation. So for Jakes model, and they all have different formula. For Jakes model, the various oscillation frequencies are given by this formula that it is 2 pi n divided by 4 times n naught plus 2, where n naught plus 1 is the number of oscillators here, which is 100, equal to number of oscillators in the J model that we are asking this. Describe. If you want more details, you can certainly go to the theory part, and there is discussion on it. So it is in lecture 30. So in like it is there in lecture 30 that how will you do a computer simulation. So you will be generating like you will be generating these sampling filters, sampling frequencies of FN. So you'll be generating oscillators and oscillate some base signals, and that is how you'll do it. So you'll have n naught plus 1 oscillators. So is the number of oscillators. So then here in the question you are given n naught plus 1 is equal to 100 oscillators, which means n naught equal to 99. So your frequencies, oscillation frequencies would be for the computer simulation, it will be Fn equal to Fd times cos 2 pi n Fd times cos 2 pi n n divided by 4 times 99 plus 2. So that is 398. Okay. So so it's 2 pi n, or I can just leave it like this, 4 times n naught plus 2, where n is equal to 1, 3, n naught, and n naught we know is equal to 99. And so f of n naught plus 1 equal to ft is equal to the Doppler frequency, which is equal to 1 kilohertz. So this is how you do a computer simulation. So you will generate n naught plus 1 oscillator starting from 0 to the Doppler frequency, and you will have all of these frequencies in your channel response. This is how you simulate, Doppler effect in the Jakes model. So I hope this is clear. So if you are told that there are these many oscillators, so you just put n naught plus 1 equal to that value, and you know n naught. And so you know the formula for Jakes model, it is given that for computer simulation, this is the set of frequencies you have to use. And so you just plug in the value, you just find these values. So you have to do some calculation here. So that is one. Okay. Now let us come to diversity, which is the main topic here. Diversity is, and let's say you are told this thing that you have, let's say, one base station, right? One base station here, base station, and you have a mobile phone like this. And the mobile phone has two antennas, two terminals, let's say, right? One terminal has this antenna, and another terminal has another antenna, something like this. You have two antennas, right? Two antennas, and so there are two parts. So at antenna 1, you are getting signal at SNR gamma 1. At antenna 2, you are getting signal at SNR gamma 2. This is the user. And you are told that there is some, uh, gamma T is like something like receiver sensitivity, right? Gamma T is your receiver sensitivity. So, and you are told that gamma 1 is less than, you are told that the signal cannot be detected individually at each antenna. So, you are told that SNR is below threshold for both antennas. You are told that both gamma 1 is also the below the detection threshold. Receiver sensitivity is also like the detection is essentially, it is defined as the detection threshold at the receiver. That if you are receiving signal with below this SNR, you will not be able to detect it. That is the idea. So, so gamma 1 is below threshold, gamma 2 is also below threshold. You are told this. Then you are asked that, so there is a, so what is the problem here? In this channel, SNR is not good enough for each of the antennas. So you need to utilize diversity, and there are two kinds of diversities here, right? You need to consider firstly diversity. You are asked, let's say, you are asked about selection diversity, right? You are asked if selection diversity will help. You are asked if selection diversity will help. So what do we mean by selection diversity? Does anyone know? So by selection method, essentially what I mean is that I will either select this one or select this one, whichever is higher. So if gamma 1 is greater than gamma 2, I will select, so essentially selection receiver is something like this. My receiver is A times Y1. Let's say I'm getting signal Y1 plus B times Y2, plus not B, 1 minus A times Y2, where A belongs to 0, 1, right? So if I choose A to be 0, then I will pick Y2. So this is A equal to 0. And if I choose A equal to 1, then I'll pick Y1. I'll pick the first antenna. So depending on value of A, I'm choosing between first and second antenna. But no matter what I choose, will it help or not? So, so if we see that in this case, if I choose Y1, which means that I get gamma 1 as SNR, because first antenna gives me gamma 1 SNR. If I choose Y2, then I'll get gamma 2 as SNR. And in both cases, so what is the best case scenario? So since gamma 1 is less than since gamma 1 and gamma 2 are both less than the threshold, which means that in neither case, in both cases, it will fail, right? No matter which one I choose, whether I choose first one or second one, both cases it will fail. Gamma 1 and gamma 2 are both less than the gamma threshold. So then this will fail. Selection selection diversity will not help, right? So this is one situation. Then you are told, you know, this one. Then same situation, if you are told that, if this question changes, something like, you are told that gamma 1 is, let's say, greater than threshold, gamma 2 is less than threshold, right? Uh, in this case, you are asked, will selection diversity will help? You are asked if selection diversity will help. In this case, answer is yes, because let's see. So if I select, I'll select whichever is the maximum of the two, right? So clearly, if gamma 1 is greater than a threshold and gamma 2 is less than a threshold, that means I know that gamma 1 is greater than gamma 2, right? Because I have some threshold, gamma 1 is above that threshold, gamma 2 is less than that threshold, right? So specifically, if I combine these two equations, what I'll get? Gamma 1 is greater than gamma t and gamma t is greater than gamma 2, which implies that um, if I take, which implies that gamma 1 greater than gamma 2, and so I'll choose gamma 1 and then gamma 1, so I'll choose this one because I'll choose between the two. So, and then this gamma 1 is above the threshold. So in this case, selection diversity is helping because I'll just, the fact that the second channel is below the threshold doesn't affect me because I'll select the first channel, which is above the threshold, and so I'll be fine. So selection diversity is helping in this case because if I had relied only on gamma 2, then my detection would have failed. So similarly, you can solve for other kind of diversities. So in this case, first case, since both are below threshold, then selection diversity is not helping. Second case, it will help. Right. Then this is one kind of question. And then you are asked, like, let's say we change this optimal diversity. Optimal diversity. Will it help in both cases? Let's say this was case 1, case A, and this was case B. Optimal diversity is when my gamma is optimal. So this is essentially something known as maximal ratio combining. So essentially, I'm being able to somehow at the receiver combine the SNRs of the two signals. So I'm being able to combine the receive signal from both antennas so that I can add them. And so now I'll combine this gamma optimal with gamma threshold, right? So in the second case, since I can clearly write greater than because so since gamma 1 is already known to be greater than the threshold, first signal is greater than threshold, which means that gamma optimal, which is gamma 1 plus gamma 2, this has to be greater than the threshold. So in the second case, it is very clear that since in the first case, I already, in the first antenna, I already have signal greater than threshold. If I add up the energy from both antennas, then I'll obviously still be above threshold. In first case, gamma optimal, it is both way possible. May or may not be greater than threshold. Because we know gamma 1 is less than threshold and gamma 2 is also less than threshold. So when I'm adding gamma 1 and gamma 2, I don't know for sure. I can either be less than or greater than threshold, right? Because Like if I take small example, if my threshold is, let's say, 2, then let's say if I take gamma to be 1.5, gamma 1 to be 1.5, gamma 2 to be 0.6, right? Then if I add both of them, in the first case, I'll get 2, in this case, I'll get 2.1, and gamma threshold is 2 here. So 2.1 is greater than 2, right? But I can also have a situation where this is, when this is 0.5 and this is 0.6, or let's say even 0.9, then if I add both of them, then this will come out to be 1.5, right? And 1.5 is less than 2. So I can have both situations. So I don't know for sure. So here we don't know. So here we don't know if optimal diversity, which is when I'm being able to add the the SNR from both of the input streams, from both of the receiver antennas. I don't know for sure. The first case I know, second case I don't know. It may or may not. But what we know is, in the first case, that selection diversity will not help. So here we know an answer. Here the answer is no. Here the answer is yes. For here the answer is yes. Second case, when one of the antennas is greater than special. Here the answer is going no. So it all depends. You have to see the situation and then analyze. Whether certain kind of diversity scheme will help or not help, right?
Sir, so what is optimal diversity do means in selection diversity, what do we do is a number of antennas are there, and the antenna which will get a maximum value of signal, that will be selected.
Yeah.
And in optimal diversity, what do we do, sir?
In optimal diversity, you do something known as maximal ratio combining. I'll tell you in a moment. Uh, so this is there in so if I talk about this is there in lecture 33, right? So what you do here is that you have some channel, and this can be proved. So you 1 second. You right. So uh, you have you have a channel and you have case streams, right? So you are, or like, let's say you have um, m antennas m antennas, and so at the receiver, what you are doing is, at the receiver, you are, each of these antennas has a receive signal r k of uh, let's say r small m t, where m is 1 to m. So each of these signals are receiving something. Each of these antennas are receiving some signal, and your combined signal is m equal to small m to capital M. You are using some kind of gain coefficient, GK, times you are adding up the signals from all of these streams, right? And these uh, these signals are nothing but some kind of complex failing. Here we're using notation Z. So I am also trying to follow notation in the lecture. So at each antenna, you are receiving this kind of signal, right? Some kind of signal multiplied by fitting coefficient plus some noise, receiver noise, right? NM of T. And so if you just put this RM of T over here, you will have this kind of a signal, right? Not K, M, BM from the next tree. So you will have something of this kind of a signal, right? GK, you have GM, ZM, ST plus summation again, M equal to 1 to N, capital M. So you just put this here, and so this is what you will get. Then GM, NM, and so what will be the SNR for this signal? This is signal term, this is noise. First term is signal term, second term is noise term, right? So your SNR will be, you will essentially be taking mod square of this. So something like modulo M equal to 1 to capital M, GM, ZM whole square times expectation of mod of S square T, which is signal power ES, symbol power, and then noise power. So this will be summation over M equal to 1 to capital M, GM, mod GM whole square, because all of them are uncorrelated. All of the noises are uncorrelated. So if you just add them, this is what you'll get times the noise power sigma square, right? Something like this. And this is SNR at the output, right? And so to maximize this, so if you want to maximize this SNR at output, what it turns out is, so you can derive it using Cauchy-Schwarz inequality, and I'm not getting into the derivation, but essentially to maximize SNR, what you need to do is you need to use these gain coefficients, Zm star divided by your sigma square. So if you use these coefficients, or divided by sigma square is optional, this is just for scaling, but essentially you need to use these. So if you know the channel, you just need to take conjugate of the channel and multiply when you are adding in the streams from all the receivers. So this is called maximal ratio combining. So there is a proof that why this will lead to maximizing SNR. So this is, that is why this is called optimal diversity or optimal combining, because optimal diversity, this is known as maximal ratio. This is there in lecture, but this is there in lecture 33. But just this is maximal ratio combined, because you are maximizing this signal to noise ratio by using this kind of combiner. So that is maximization.
Okay.
So if you are
sir.
using this, if you put in this value, you will get the Zm star. Zm will give you mod Zm square, right? So you will get mod of summation over M equal to M. So you'll get something like this. So that is why, so then it becomes, now if you take mod Zm square is equal to gamma M, so you will get summation over all SNRs, gamma M. So you are essentially adding up SNRs from all the streams and for this kind of logic system. That is what you do successfully. This maximal ratio combining, and then there are selection, and there is another thing called phasing. So you can all of these are there in like lecture 32 and 33. So many of the questions in my section are just plain theoretical, and essentially if you read the lectures, you have the answer in the lecture itself. It's MCQ type especially. So that we should try. Now let's do another conceptual question. So you are told that Where is this? This was question. So use numbering type. Now you're told that output SNR, like that you have, let's say you are told that you have selection diversity at receiver, right? You have selection diversity, and you are told that uh, output SNR, out, um, you are asked to find the, so what is the probability that your output SNR, um, output of selection diversity scheme, output SNR is uh, is lower than, so you have some average SNR, it is lower than average SNR, so this is value in dB. It is lower than average SNR by something, by 10 dB. Average SNR of each branch. Where gamma is nothing but average SNR of each branch. Let's say you have a selection diversity system where all of the branches have the same average SNR, same average SNR gamma, and you are selecting. You are selecting between these branches, right? So in a relay fading system, you are asked to find that your selection diversity scheme will give you an output. You are asked to find the probability that your selection diversity scheme is giving you SNR below this, below, like it's 10 dB below the average SNR. So let's say gamma dB. Average SNR is 10 dB, right? So what is the probability? So so let us denote this as gamma threshold. So we want the probability that gamma selection diversity is below this threshold. So gamma threshold in dB is equal to this 10 dB below the average SNR of each branch. Again, pictorially, what do we mean? We have like here is essentially we have base station and we have mobile on some user, and let's say there are also I need to mention, okay, so let's say uh, assume like let's say two identical antennas. Assume that there are two identical antennas. So at receiver end you have one antenna here and you have another antenna here. These are identical. Both are receiving like similar kind of signal. So both are receiving signal at average SNR gamma, right? Average SNR is gamma. And there is fluctuation like relay fading. So here at output, you are essentially seeing that, okay, gamma 1, gamma 2, and your selection diversity scheme, what does it do? Gamma SC is equal to max of gamma 1 and gamma 2, right? You'll choose whichever is the better. And you're trying to see that this is below a certain threshold, which is your average SNR minus 10 dB. So in linear scale, gamma threshold, in linear scale, this means that if it is 10 dB below it, it means that that the ratio of gamma threshold divided by this gamma, because this is just like 10 log times of linear scale. So if we remove log and see the actual value in linear scale, this will be nothing but 10 to the power minus 10 by 10. So I'm just converting decibel to linear. So this is 10 to the power minus 1 times the threshold. So this is gamma threshold value. So this is the ratio of gamma threshold by gamma. And we have to remember that for each of both gamma 1 and gamma 2, both gamma 1 and gamma 2 are nothing but uh, gamma 1 and gamma 2 are both Rayleigh filling. So these are all exponential random variables with mean gamma, right? Exponential random variables with mean gamma. And so probability that, you know, gamma SC is, this thing. What is gamma SC? Gamma SC is probability that that max of gamma 1 and gamma 2 is below gamma threshold, right? Because that is how I've defined selection combining, right? That I'll choose the maximum. So if the maximum is below threshold, it means that both of them have to be below threshold. So I can write this probability as probability that gamma 1 is less or equal to gamma threshold and probability that gamma 2 is less or equal to gamma threshold. I need both of these conditions to hold, right? Because if any one is false, it means that maximum is greater than threshold. So for max to be less than threshold, both of them have to be less than threshold. So for that, what I get is, so since both are exponential random variables with mean gamma, so this probability is actually something like, you can calculate, it will come to be 1 minus e to the power gamma threshold by this mean gamma. And this will be for both. So I'll just square it. We both have identical distribution. And then I know gamma threshold by gamma. I have to calculate it here as 10 to the power minus 1 because it's 10 dB below. 10 dB below means that it's 0.1 times the 0.1 times the value. So then if I plug it here, so this will be 1 minus e to the power minus, 10 to the power minus 1. Sorry, there's a minus in. So then this whole square. If you calculate, you will get the value. I hope this was clear. This derivation is very simple, like exponential variable is this, and so like e to the power exponential variable with mean gamma is 1 by gamma e to the power minus gamma by f gamma. This is the PDF. If you integrate over, all gamma, and you want it to be below a certain gamma threshold, you can just calculate and see that this integration will come out to be. So this is the result of that integration, and you can just then you can just plug it here. So you will get this output. So I hope this kind of problem is clear. Right. Any question you might have, you can ask. I'll take a short break and I'll come in 2 minutes. Please come back in 2. you're told that this error probability in AWGN channel, AWGN channel is something like you can take any number really. Um, you can you're told that this value is something like 7 into 10 to the power minus 6. So if you send a BPSK symbol on AWGN channel, you're told that this is the error probability that you can get. Right? And you're told that you are using a receiver with 4 RX antennas, right? You are using a receiver with 4 RX antennas. Uh, and um, so this is probability of error in AWGN channel. You are told this is with one antenna. So if you are using only one antenna receiver, then this is your error probability. Right? So this is a simple situation. TX, RX both has one antenna, transmitter and receiver, and now you are said told that now you are using four antennas with selection combined or selection layers. You are told that you have four antennas with selection diversity. Now, you are using this to combat relay fading. In relay fading scenario, because why do we need diversity? To combat fading, right? If there is fading, then we need diversity so that we still receive the signal instead of fading. And you are told that what is the outage probability? You are asked what is the outage probability now for the daily queue, right? So this is the probability of outage or probability of error in AWGN channel with one antenna received. Now you are asked what is outage probability in relay fading channel with four antenna receiver, where you are using selection combining, and you are told that minimum SNR for minimum SNR that you require is 3 dB. Minimum SNR for successful detection or whatever. For successful detection at receiver, you need minimum 3 dB SN at receiver. So you are asked what is the outage probability? What is the probability that I will not be able to meet this 3 dB minimum SN? If I'll be going below 3 dB. How do we solve this kind of problem? So firstly, let us calculate the AWGN channel itself. So I know that probability of error for AWGN is given by Q times for BPSK symbols. So it is given by Q times 2 root over gamma AWGN, where gamma is the SNR. And I'm told that this value is 7 into 10 to the power minus 6. So this will tell me, so from here I can calculate gamma AWGN. So I have to use online calculators to take, so this will be essentially half times of Q inverse 7 into 10 to the power minus 6 whole squared. Right? So if I take Q inverse and then square it and then half it, so that is it. And so let us calculate that using, I'll just use MATLAB. But in your exam, you can expect either you are provided some, online table or you are just given your value. But I'll since I'm cooking up the numbers right now, so I'll just use the MATLAB function. So let's see. 7 I'm getting this value to be something like 9.43. That is the SN 9.43 approximately. Now, why do I need this? Because in relay fading, right, I need to find the average SNR. So I need to find the average SNR in relay fading, right? How do I find that? So, so this is nothing but, see, I had explained earlier, right? So this is nothing but expectation of the fading gain times gamma AWGN, right? Because in AWGN channel, you have y equal to x plus n. And here you have y equal to some zx plus n. So that is the difference, right? This is AWGN and this is relay fading, right? So, so if you take average of this, then you will have expectation of this mod z square times the normal AWGN SNR. So expectation of mod z square normally, if nothing is mentioned, we'll assume it to be 1. So we take expectation of mod z square for relay fading is equal to 1 if nothing is mentioned. If nothing is mentioned. So yeah. So then we'll have gamma relay equal to gamma AWGN. So this will also be like 9.43. All right. So now for see, for two antennas, this was the formula, right? By same logic, if you take max of, now you're told that there are 4 antennas, receive antennas, or for n antennas in general, if you take max of gamma 1, gamma 2 till gamma n, less or equal to threshold, by same logic, you'll have probability gamma 1 less than threshold, gamma 2 less than threshold, all of them have to be less than threshold. So we'll multiply this term. So this will become, instead of 2, this will become to the power n. So it's 10 general for n antennas. So for 4 antennas, this outage probability, that probability of after selection combining, probability of gamma SC to be less than gamma threshold is nothing but 1 minus e to the power minus, this gamma threshold divided by average whole to the power 4. Because you have 4 antennas here. You're told that there are 4 antennas, right? And you know that, now what do you know? So you know that gamma threshold is 3 dB, which is, you're told that 3 dB is the minimum SNR. So that is your gamma threshold for detecting. This is 10 to the power 0.3. Approximately this comes to be 2. So you can just plug in the value and you will get this 1 minus e to the power minus 10 to the power 0.3 divided by 9.43 whole to the power 3. You can simply calculate and you will get your answer. So this was one kind of question. I hope this is clear. Normalized capacity of channel with free space path loss. Free space path loss. Okay, so free space path loss plus fading. So you want to go in that direction. Still, I don't know which. Normalized capacity. Could you explain, like, what do you mean? I'll move on for now. Let me cover the other more important topic, which is different kinds of. So some formulae are important. So we have this notion of diversity gain. Gain. What is diversity gain? It is, we take log of this thing. log of SNR output divided by log of SNR input. So something like this is known as diversity gain. And as I'm skipping the derivation, but so if you just derive, so we know the bit error rate only for various fading, for various kinds of fading. So like essentially, what is the gain in the SNR that I'm getting for the output versus the input? So for if I assume if I have M RX antennas, M receive antennas, then diversity gain for maximal ratio combining is M gamma is M times the average SNR, right? Diversity the diversity gain, if you see, gamma MRC by the average SNR input is M. For selection combining, which we have discussed a lot, this is 1 plus R plus 1 by N. So these are all, these are derived in lectures 32, 33. Mainly 31, 32 actually. You can check it. So, after doing these combining, what is the gain in the SNR in DBC? That is what we are trying to see. And so if you just put in the value of M, you can get these diversity gains. And then there is a third one, which is co-phasing approach, where this diversity gain is 1 plus M minus 1 times pi by 4. So as you can see, for a general so you can actually calculate depending. These derivations are there in your lectures, but you can calculate these. And so let's say you had asked M equal to 4, M equal to 5. What are the various diversity gains? So for MRC, it is 5. Co-phasing, it is this 1 plus 5 minus 1, 4 pi by 4, so 1 plus 1 plus 5. And for selection combining, it is 1 plus half plus 1/3 plus 1 by 3 plus 1 by 4 plus 1 by 5. So that is it for selection combining. Now, so what do we mean by co-phasing here? So ultimately, this is the general form, right? So my receipt signal is if I have N antennas, so I'll be summing over the outputs of all of the N antennas, right? So all of the N antennas will have this kind of signal, right? Some fading time signal, some fading time signal plus some noise, Ni of t, right? And so in co-phasing gain, what I try to do is I I multiply it with the negative of the phase. But which phase? So here each fading gain, these are complex numbers. I can represent this as magnitude times phase. So if I know Zi, then I can just nullify the phase part. So I can just multiply it with e to the power minus j pi I. And so what happens is, for all of the Zi's, then I am able to somewhat remove the phase and add them in a coherent manner. Right? So here, like essentially, what I have is something like mod z1 plus mod z2 plus mod zn, this whole thing times f of t plus some noise term. So if you actually do the calculation, you can. So for this co-phasing approach, why is it called co-phasing? I hope it is clear, because you are removing the phase component by just multiplying it with e to the power minus j5. So the phase cancels, and so you add up the magnitude. So everything is in the same phase in a way, and so that is why it is called co-phasing, and you can calculate that expected that this gamma co-phasing on an average, this will be something like 1 plus, if n is the number of antennas, n minus 1 pi by 4 times the average. So you can calculate this. And so this is another kind of diversity that we have. So just standard formulae that you can use. So that's it for me. Now this remaining question, could you explain maybe a little bit if you want? Because free space path loss. Okay. So in general, um, like you will have something like y equal to your receipt signal. So y equal to h times x plus n, right? So here this h is fading coefficient, and so there are two parts to the fading coefficient. We write it as something like root over beta times h tilde, and don't think this has been covered fully yet. But so this beta part is so this is Rayleigh fading model, right? Rayleigh fading. So unless otherwise mentioned, beta is 1, but beta part actually depends on beta is essentially your free space path loss. Free space path loss plus shadowing. If you don't include shadowing, then it's just free space path loss. And your h tilde is a so this is complex normal random variable with mean 0 and variance 1. So this is how Rayleigh fading is modeled. Now, if you want normalized capacity of channel with free space path loss, I don't exactly know what you are referring to. You can you can calculate capacity of fading channel. So you can calculate capacity of fading channel, which is if you take average of SNR, you essentially this is expected value of log of 1 plus mod h square, this thing, right? Signal power divided by noise power. So this is your expected value of the capacity. Log of 1 plus SNR, this is by Shannon theorem, Shannon law. And SNR is mod h square, signal power by noise power. Now, if you take Jensen's inequality, then this will be, then we can write a lower bound for this to be 1 plus expected value of mod h square t by n now. So then this is a lower bound. Now you can use this as some kind of measure. So now expected value of mod h square is, let's say, this you can write it as maybe log of 1 plus, see, h square is root over beta times h tilde. So see, expected value of mod h square is beta times expected value of mod h tilde square, right? And expected value of mod h tilde square is 1. So this is equal to b. So we can get lower value as this beta p by n naught. And so if we can divide it on both sides, and we can define some kind of normalized capacity as C fading divided by this log of 1 plus beta times p by n. So we can see how much above it is. So we know that lower bound for this fading capacity is because log is concave function, so expectation of the Jensen inequality is there, right? For concave function, that expectation of f of x is greater than equal to f of expectation of x. So this is Jensen inequality. So using that, this is a standard probability and statistics. So using this, I have written it here. And so we know that this is a lower bound. And if we divide the lower bound, we can get some kind of normalizing. Now, I'm not sure if this is what you are referring to. This was my guess. So then you can have some kind of normalized capacity. If you're doing simulation, you can calculate expected value over all simulation iterations, instances, and then you can divide, because this is deterministic quantity, so you can just calculate and divide. So, any other question? Otherwise, my time is over almost. Any other question doubts that you have? Otherwise, I'll end the session. Thank you. Bye.